Hey guys, we're going to talk about soundings today. I'm going to give you a sounding that you're going to have to know all the parts to. So this is going to be a review of something that we did the other day. Uh, Everything on here is vitally important, so you need to watch this once, twice, 3 times. In other words, get this done really well, okay? So we'll start here. I will start with my screen, and we are going to start with the sounding. Okay, so the very first thing, obviously, we need a dot that is the temperature, and we need a dot, I'm going to put it far enough away, that is the dew point. And all of this is coming true at some, let's make that smaller. I'm going to go do this at some pressure. Okay, so that's an isobar. And the idea is this, we always have to be given that information. So whenever I see this, I'm always going to take a sounding. I'm going to take a dry adiabat. And I will always draw the dry adiabat. And I will always draw a mixing ratio line from that. And I'm going to go up a long way, okay? And there's a reason for that. So a couple things that we know, this line is W, that's your dew point. This line is your, or this dot is your temperature. This line is your theta. Now keep in mind that the dew point Bob gives you is actually all over the place. So we would have a bunch of points, whatever that happens to be, and we plot that up. And we may need this for other information. Later on in the lab, we may go other parcels, other places, figuring out theta. But we'll see the plot of temperatures. Likewise, we're going to see the plot of dew points. Likewise, we're going to see the plot of temperatures. Now, I'm going to kind of draw this on here. Okay, and we might get something like this. Maybe we could even come back here as an inversion, and we get temperatures going up like this, dot, dot, dot. And so for the sake of simplicity, I'm just going to draw in that temperature sounding. That's what Bob measures. And that goes all the way up. Now, eventually, we're going to start to get up here where the temperatures change considerably. That would be the tropopause. Okay? So anytime we have the tropopause, goodness gracious. Sorry about that, guys. It'd be nice if I could spell. Let's try it again. Tropopause. There we go. Okay, and that's where the temperature is pretty much the coldest, something along those lines. Okay. Now, when we do this, we know that we're going to lift a parcel. So the parcel will always be in blue, and it will be dry adiabatically up to there, and then wet adiabatically past that. Okay, so it's a dashed line on the thermodynamic diagrams, but obviously this is hard for me to do this on this pen. So what I'm going to do is just try to make it a little bit straighter. Something along those lines. Okay, so be careful here, okay, because you want to make sure different. Remember, this mixing ratio line is showing you the dew point of a parcel if you lift it, and it's sloped at 2 degrees Celsius per kilometer. Whereas this line is going to be, the dry adiabat is at 10 degrees Celsius per kilometer. So we have the isentrope, or the dry adiabat, which is a line of constant theta. And then we have the parcel, and we see that the parcel, and we can draw that in blue here, is going to be starting out similar to the environment. Then it gets colder than the environment. Over here, it's going to get warmer. So when I see that it's getting warmer, I go in here and I go, well, that's the LFC. Keep in mind that when we go from dry to wet, that's always the LCL. Now, over here, the parcel gets colder. There's an inversion here. And so what we get is we get an EL. There's another one, that's an LFC. And then over here, it's colder than the environment, and therefore that's another equilibrium level. Obviously, this is above the tropopause, so we know that's up in the stratosphere. Now, what we would do is we would shade in these areas, and I'm going to do this really quickly with you and then erase it because I don't want it to get kind of messy. Okay, so I don't know what we call, I guess we're just shading it. Oops. I can shade it in orange. And I can shade this in orange. And I can shade all of this in orange. So it's going to go up here quite a bit. And then that's going to be all negative buoyant energy. And then the positive buoyant energy is this big area of Cape there. And then this area of Cape there. So the purple is the PBE or Cape. The orange is the NBE or the convective inhibition, this one especially. Now, keep in mind that when you're looking at a sounding and you're talking about these things, you should always have space between the environment in red and the parcel in blue. Keep in mind that the parcel is always a dry adiabat followed by a wet adiabat. Okay? Now, I'm going to go ahead and undo those shaded in areas because if I make a mistake, it'll make it bold like that. So I don't want that to happen. Now, I'm going to go over here and I'm going to tell you something more about the wet adiabat. The wet adiabat here is, the value of it is theta E. So the value of the wet adiabat at the LCL. But I want to point out something, that this wet adiabat continues to come down to the surface. So I'm going to draw this in very carefully here. This is a wet adiabat. From the LCL to surface. Okay, that is going to make a point, and that point is TW. Excuse me. That stands for the wet bulb temperature. So that is that. You go from the LCL down to the wet bulb temperature. Now this is the wet bulb temperature. Couple of things. If you look in your glossary, the wet bulb temperature says it's the temperature that air cools to because you are evaporating water. Most important thing here, though, is the temperature of a raindrop. So if I can give you the dew point and the temperature, I can go up here, tell you what the wet bulb temperature is. And the wet bulb temperature tells me what the temperature of a raindrop is. So if it's raining and the wet bulb is very cold, the rain is going to evaporate, it's going to be very cold. If it stays fairly warm, then it won't be that cold pool. In the wintertime, if this drops below freezing, then we start to get freezing rain if the raindrop is melted. So it's an important factor. So this is important, and you need to know that. Now, couple of other things here. I have taken the mixing ratio line, and this time I'm going to redraw it as a little bit thicker of a line and in a brighter green. So I'm going to go up this line here, and it intersects the observed temperature sounding. Remember, the observed temperature is the red line. It's the squiggly one. It's the one that Bob's telling you. Notice that that green line, and I'm going to do this one more time because I said I was going to make it thicker. Why are you the wrong color? There we go. I'm going to make it here. It intersects in three places. Right here, and right here. All of those intersections of the constant mixing ratio line through the dew point with the observed temperature sounding, that becomes what we call the CCL, which stands for the convective condensation level. Not the lifting condensation level, but the convective. In other words, if I heated the ground, and we're going to talk about this in class, the air will mix up there. You'll start to get these eddies. Basically, you're saying the air is going to start convecting on its own. And if it goes up because of heating, you get condensation. Basically, this is the base of a cumulus cloud. So what we would expect to see in a sound like this is if you heat it enough, you're basically saying that the temperature of the environment will go dry adiabatic. We'll explain that later on. But this is where I would expect there to be the base of a cloud, a cumulus cloud. So it's technically, the LCL is lifting it. This one becomes where the cumulus cloud is. And just to give you some idea, what I'm saying is if you warm the air, you're going to rechange this environment profile so that it becomes like this. So this goes away, it becomes this straight dry adiabat. We'll explain that in class. So I'm not going to get caught up on that right now. But I do want you to know that's what it's about. Now, technically, this is not a CCL, this green line here, this intersection, but this is a second CCL. So if you put all three of the green lines is a CCL, that would be fine. In the notes, in the lab, it says, all right, then go dry adiabatically from the CCL down to the surface. And that dot right here is what we call the convective temperature. So there's 4 dots you need to know on this sounding: convective temperature, temperature, wet bulb, dew point. Bob gives you the dew point and the temperature. You can easily calculate the wet bulb. You have to find the CCL, go dry adiabatically. In the notes in the lab, it says down to the surface isobar level. That's this yellow line here. That's the convective temperature. You're basically saying, if I could warm it to here, I'm going to get a cloud. Now, since there's more than one, there'd be more than one CT, which is fine. So this one over here, if I did that, not only would I get a cloud, but notice that now the LCL and the LFC and the CCL are all the same, and it's all instability. So in other words, if I get to the topmost CCL, just by heating the ground and changing the atmosphere, I'm going to get a thunderstorm. So I heat the air enough to get a thunderstorm all by itself. And this can happen, especially in the summertime where there's really no convective inhibition. You just heat the air, it's humid enough, and boom, you get some afternoon thunderstorms. So this probably will make more sense when we get to boundary layers. That's my hope, is that it'll make more sense physically, but you should be able to know how to do this at this point. All right, now let's go here. Let's say that this line is 500 millibars. That's usually considered the beginning of the atmosphere. This is the parcel temperature at 500 millibars. This is the atmospheric temperature at 500 millibars. So what we say is that the temperature of the parcel is that temperature. The temperature of the environment is that temperature. And the lifted index, if you look at it, says it's the temperature at 500 millibars. So that's the environment, that's what Bob gives you, minus the temperature of the parcel at 500 millibars. The only thing is, this is a parcel lifted from the surface. The parcel lifted from the surface. And that's the parcel we always draw that surface parcel. Now, in the notes, it says that the Showalter index, which is the same formula, the only difference is this is a parcel lifted from 850 millibars. So how do you lift a parcel? Okay, now it's going to get a little bit messy. All right, so watch this. I'm going to take a straight line, and I'm going to say, let's say that this is 850. Okay, 850. The temperature of the parcel is in red, and I would go up dry adiabatically from here. Draw in a dry adiabat. Draw in a mixing ratio line from the dew point at 850, which is here. Then the parcel is lifted from the temperature, dry adiabatically, oops, to the new LCL, which I didn't do a good enough job here. Right, there it is. And then I go up wet adiabatically up here like this. It's going to be curved. So this difference is the Showalter index. So go through this a couple of times so you figure it out. The only difference between these two is that the parcel temperature is calculated with the parcel that we lifted from the surface. This one is lifted from 850. So what did we need? We needed the dew point at 850, which is that point right there. And we needed the temperature at 850, dry adiabat, mixing ratio line, wet adiabat. Okay, so I think I can erase most of these things. I'm hoping to get it back to where I need to be. Okay. But everything's up to 500 millibars. Now keep in mind that the wet adiabat, eventually, we said this, and Ben, you were talking about it, goes parallel to the dry adiabat. So if I came back all the way here, right, that's dry adiabat. Do you agree that's a dry adiabat? And that value of the dry adiabat is theta E. That's how we did it. The wet adiabat becomes parallel, the dry adiabat, and the value of it. So, but remember that the line, the wet adiabat, is labeled theta E. So this line is labeled the same as this line is once they're parallel. Other thing that's important is this, that the difference between the temperature and the dew point that's here, temperature minus the dew point, that's known as the dew point depression. All right. So those are the things you need to know from this diagram. It's a lot of lines. So what I do, what I really want to do is I'd like you to do this, save this image, open it in some paint or whatever you're using, and make it a black and white image, because on a test, it will be a black and white image that you have to label. Just remember the points, the LI, the Showalter, theta E's, lots of things on here, and you shade in the areas. So it's going to be a messy graph, but I should be able to determine that if you do it right. Okay, now one more thing. Remember how I did the Showalter index right here? You need to remember this, really important for the lab. The Showalter index, when you're doing part 2 of the lab, plot up you don't even have to plot up the temperature, just on a separate sheet, a separate diagram, plot the temperature and the dew point from 850, that temperature, that dew point at 850, and then calculate the temperature of the parcel. The temperature of the environment is, you don't have to show it, it's given to you. But the temperature of the parcel, you need to know. Now, this is intense. This is what you need to know. If you know this and you're like, I get this, I'm comfortable with all these things, you're going to be just fine. If you're not, there's a problem. So because it's on a tape, it's on video, not a tape, on video, you have the ability to learn it. We've done it in class, but you go through this a couple of times. And if you have a specific question, let me know. Okay, now a couple of other things I want to show you is in the notes, and I'm going to start like this. So I'm going to go here. I'm going to go to our notes. These are on Blackboard for you, but I've also got it here. So it says static stability. I can open this up and it gives me these other indices. So this other one is a K index. Now, let's do this. I don't need this anymore. The K index is simply a formula. Remember, we need lift, moisture, and instability. Instability is a race to get cold between the parcel and the environment. So slow parcels, but a lot of times we can say fast environments. So if I look at the temperature at 850 minus the temperature at 500, this is of the environment. That is the lapse rate from 850 to 500 millibars, and I want that to be large. That's the environment cooling quickly. The lapse rate is the rate of cooling. So lapse rate is large from 850. So if I get this number large, then I'm going to have a high K index. Then I add the dew point at 850. So that gives me moisture, adding the dew point. Now this one is subtracting off the dew point depression. Remember, the dew point depression is the difference between the temperature and the dew point at 700 millibars. So make sure you take the difference, put it in here, and then take away what's in the parentheses. Pretty straightforward. You're looking at the numbers that I give you, and there it is. Okay. Now, dry air at 700 millibars makes this number big, which makes this number small, since I'm taking away a big number. So I could get a low value because of dry air. But remember, we said dry air at 700 millibars can be good for large hail, for damaging winds, and something we call convective instability, which we're going to be getting into. So K-index is not good for severe weather. Poor indicator of severe thunderstorms. But it's something that we deal with. If the numbers are high, it usually means we're going to have a lot of rain. Okay. Now, that's one. The total totals is kind of a weird name, right? So what we said is, well, I'm going to have something called the vertical totals. And somebody said, now, I'll tell you about this in a second. Somebody said, hey, let's just take the temperature at 850 and subtract off the temperature at 500. Do you agree that is the lapse rate? That's what we see here. So this is actually the vertical totals. And that's what we see here in the vertical totals. Then we have something called cross totals, saying, well, you know what? I need to have humid air at 852. So instead of that, I'll just take the dew point at 850 and subtract off the 500. So it's crossing from the dew point to the temperature. Somebody said this. But if I add those two together, I get the temperature at 850 plus the dew point at 850 minus 2 times the temperature at 500. And then we call that the total totals. So the vertical totals plus the cross totals is the total totals. This is kind of nice. It's a quick way to see if the air is moist and unstable, if there's steep lapse rates. None of these indices are going to deal with lifting air. So we lift, moisture, and stability. There's no index to talk about lift. Now you may say, well, why are these numbers? Why are they this way? Why? That seems weird. If you look at the next one, when we go to the sweat index, those are weird numbers to put in there. Okay, all of these things are what we call, big dot. That would be, they're empirical. Empirical means we have figured this out from experience. Back in the 50s, 1950s, there was a big experiment. We were just trying to understand thunderstorms, and that's where they came from. So they said that 850 millibars was low level, 500 millibars was mid level, and those are what really matter. The 700 is a little bit in the between, but that's what we figured out. That's what they said. And then, like for the sweat index, they said, well, let's put this number in. It seems to work out. By experience, it seems to work. And everybody went, okay, fine, whatever. And it's just kind of caught on. It's nothing special. Now, if I have the first law of thermodynamics, right? That when you have laws of science, anything derived from the law of science, the dry adiabatic lapse rate, those are good statements of true things. Empirical is just to help you understand. It's not nearly as important as anything derived from the first law or from a law of science. So the hydrostatic equation, instability is all derived from basic principles. This is empirical. We said, hey, this seems to work. Okay, so sometimes you'll have a high total totals and there'll be no thunderstorms, whatever. Okay, just a way to do this. So the last one is the sweat index. And the sweat index is interesting because it stands for severe weather threat. So we said we had lift, moisture, instability. There's no lift. We had moisture and instability. But now we want to do the last thing for severe weather, which is vertical. Oops. Vertical wind shear. So we're adding in some shear terms. So the first thing we do is we say, hey, the sweat index is this formula. Now, guys, you're going to have the formula on the test, so you don't have to memorize this. I give it to you. It's available for you. So just you have to know how to use it. So all it is, it's 12 times the dew point at 850. Remember, this is all environment, not the parcel. This has nothing to do with the parcel. You don't need the parcel. So I have the sweat, 12 times the dew point at 850. Then I say, well, what's the total totals? And then I subtract 49 from it and multiply it by 20. Again, empirical, weird stuff. I don't know why that's the number. That's just what they said. It's kind of weird, even to me. But there it is. Then it says 2 times F at 850. Well, F, if you read here, is the wind speed in knots. So you look at the wind given to you, Bob gives you that, and you say 2 times the wind, as long as it's in knots, okay? Then you have the wind speed at 500 millibars. And then this last term. And we're talking about this. This, by the way, this is what I mean by a term. Any place in between the plus signs. That's a term. This is a term. And this is a term. And it gives you some ideas of what to do with those terms. It says the first term is set to 0. So in other words, no matter what it is, if the dew point is negative. So you never have a negative value in here. 0 is the least it'll be. And then you just plug it in here. And then the total totals. And it says that term is set to 0 if total totals is less than 49. So again, no negative terms. These two are always in there. And then this last term. So what is this last term? Let's talk a little bit about that. It says S is the sign of the 500 millibar wind direction and 850 millibar wind direction. So SIN, sin is called sine. It's a sine function. Basically, it's on your calculator. So what you need to do is, if you have a calculator, great. If you're using your phone, turn it sideways and you get sine. And you just need to make sure that whatever you have, if you plug in 90 and hit the sine button, it should come out to be 1. If you have a calculator, take the sine of 90. If it doesn't say 1, if it says 0.866 or whatever, that's because you're in radians. You need to convert it to degrees. So you need to switch the input to degrees. You should know your calculator. If you've got that sophisticated one, you should know how to do that. So using degrees. So all you're going to do is you are going to take the direction. This is not the wind speed, but the wind direction at 500 millibars. So let's say it's 240 degrees. And then minus the wind direction 850. So let's say that's 190 degrees. You take the difference and you're going to take sine of 50 degrees. Now I happen to have my calculator right here. Clear this out. I'm going to take the sine of 90 degrees and I get 0.766. So we go 0.766. Okay. That's what you plug into this. That's what S is. But what do you do after S? You add 0.2. So we add plus 2. So we get 0.966. And then, please excuse my dear Aunt Sally, then we multiply by 125. And that is what this term is. But it says the last term is set to 0 if any of these is not met. So you basically say, well, okay, if I'm going to ask these as questions, is that direction between this? Is this? Is this? Are both the wind speeds? Okay, so those are questions. If you say no, then this term goes away. Okay, this term goes away. Now let's see. We have in this one, we'd say, is the 850 millibar wind direction between 130 and 250? I said there's 850. The answer is yes. Go to the next question. Is the 500 millibar winds between 210 and 310? Yes. Is the 500 millibar minus the 850 greater than 0? So 240 minus 90 is 50. Yes. Are both the wind speeds at least 15 knots? I didn't give you that, but that's what you find out. If they're under 15, the term goes away. So again, like everything else, and I know that some of you will take it open notes, this is always going to be given to you. Okay, so there's the word empirical, and that's how we do these things. Okay, so read through this stuff. It's pretty straightforward. Let's take a look at one. I'm going to show you one more thing here today so we can practice those. I'm going to go to where my weather analysis tools, and I'm going to go to upper air soundings. We happen to have a severe weather event going on here. So I go here, I can go to my text program, and I'm like, look. And the first one is I want to know the K index. The K index. And we said the K index is the temperature at 850 minus the temperature at 500 plus the dew point at 850 minus the dew point depression at 700 millibars. So I need to look at the values here, and I'm like, okay, wait a second, let's do this. I'll go to yellow. I'll go, here's 850. Here's 700 because I'm going to need that, and here's 500 down here. Okay, and I go, all right, what's the temperature at 850? And I just simply put it in. Equals, oh shoot, I hate when I do that. Oh, whatever. I get the temperature at 850 is 13, and the dew point's minus 8. So 13 degrees plus minus 8. And then what's the 500 millibar temperature? 500 millibar temperature is here. And it's negative 16.1. Minus negative 16.1. And you add those together. You get minus a negative is plus. So this is 29.1 minus 8. Sorry. That's for this one. So 29 minus 8 is 22.1. And then the dew point depression, 700 millibars, that's here. It's 7 and negative 18. That's a 25-degree dew point depression. So 22.5 minus 25. And that becomes negative 2.9. Wow, that's really low. Okay, so if you look at this and I go down here to the bottom, I can look at the K-index and I say, oh, negative 3.9. Did you catch that? Negative 3.9, because, yeah. I think 29 minus 8. I must have done something wrong. I'll deal with it. But you can always come down to the bottom and it'll tell you things. It also tells you the sweat index, the total totals index. So when I'm giving you assignment, you're going to get these. So what I'm going to do for you is I'm going to give you an assignment. And I'm going to look at the sounding. Let's, first of all, I guess I got to find out what's going on. Yeah, this should be okay. Okay. So in here, mark temperature at 850. Yeah. Hold on. I want to maybe do another one. I'm trying to find you one where there's severe weather, but it's, let's go to Miami. How about that? Yeah, that'll work. No, it won't work. It's really dry every place. How about Brownsville? Yeah, that'll work better. Okay, let's just try this one. So here at 850, mark those numbers. Temperature is 24.4. The dew point is 1.4. Okay, and then the wind, if you look over here, the wind direction and speed, it's 885 degrees at 22 knots. So you need to have this information. It's on a tape, a video, so you can go back and get it. Here's 700 millibars, 12.6, negative 6.4. I don't think you need the winds on this one. 500 millibars, you do need that. You need negative 10.7. That's the dew point. I don't think you need that. And then the winds are 275 degrees at 20 knots. Okay, and then what I want you to do is I want you to calculate based on the charts to practice and bring it to class next time. I want you to do the LI, the SI, the sweat, which you'll need the totals. So the totals and the K index. Do those 5. By the way, just so you know, here's the answers to those. There is your lifted index. There is your Showalter index. There is your vertical and cross totals, and there's your total totals. There's your K, there's your sweat index. So go ahead and calculate them to make sure you know how to do this. And then in class, we can discuss it. So you've got the answers right here. You can always go back to the video. I'm going to stop the share and I'll say goodbye because that should be a good explanation. This is how you do stuff. In class, we'll have more of a discussion, but this is just basic how to do stuff. And you need to know how to do stuff. Okay, guys, have a good one.